In this class, we will see how exhaustive search can be done with recursive backtracking. It is quite a mouthful, the title. It needs some unpacking. We are searching for a solution in a state space, or we are searching for a solution which is optimal. Therefore, the problem may be either a search problem or an optimization problem. However, we still call that exhaustive search. So one of the simplest points that you have to take note is, even though I call it exhaustive search, the problem is not necessarily a search problem. It may be either a search problem or an optimization problem. In the last class, we took a look at graph traversal algorithms. Suppose we are given a connected graph, or for that matter, we are given a graph and a source vertex. We are interested in finding out all the vertices which are reachable from the source vertex. The source vertex is S, and there is another vertex V. If there is a path from S to V, the vertex S to vertex V, then we say that S and V are connected, or V is reachable from S. We said that there is a template algorithm. We call it in a funny way, whatever first search. These graph traversal algorithms use a bag to remember the vertices they have discovered but not yet explored. A bag is a data structure like a set. In the place of a bag, we use a stack. Whatever first search becomes depth first search algorithm. For a bag, if you use a queue, whatever first search becomes a breadth first search algorithm. In the place of a bag, if you use a priority queue or a heap, it becomes the best first search or priority first search algorithm. So that's what we saw yesterday. How we can traverse all the vertices of a graph, or how we can visit all the vertices of a graph reachable from a source vertex. Then we said that suppose the problem can be formulated in a state space. We can search for a solution in the state space using any of these graph traversal algorithms. State space is a graph. Only that a graph is explicit while a state space is implicit. When I say a graph is explicit, the entire graph is available upfront, all the vertices and edges. Maybe the graph is represented using an adjacency list, whereas in a state space, there are no vertices and edges upfront at the outset. When we start, we have only an initial state. Every state is represented by a vertex. In a state, we can take actions. When we take an action in a state, we are led to one of the successor states. So this taking an action is represented by an edge. So states are represented by vertices and actions are represented by edges. As we keep taking actions in every state, vertices and edges are generated. So it is more dynamic. As vertices and edges are generated, we traverse the graph. So that's a summary of what we saw yesterday. Now we can search for a solution in state space in a number of ways. We want to do exhaustive search. In every possible way we want to search the state space. But we want to narrow it down or restrict it to a specific kind of problems. I will tell you what is the kind of problem in the course of the lecture. When the nature of the problem is restricted to some specific kind, as we are going to discuss, we can do exhaustive search with recursive backtracking. You have already met this word backtracking a long time ago or some time ago when we discussed about enumerative search. But in this lecture, we will take a thorough look at how recursive backtracking works. This is the overview of the lecture. Exhaustive search in a state space graph. In general, suppose the state space is a tree. Then we can use backtracking. Suppose the state space is a tree and the state is represented as a vector, then we can use recursive backtracking. Look at that. In stage 1, we have a state graph. Then we say we can do exhaustive search. If the problem is restricted to a state tree, then we can use backtracking. If the problem is further restricted to, it is a state tree and the state is represented by a vector, then we can use recursive backtracking. You would have noted I make a distinction between all these three terms: exhaustive search, backtracking, recursive backtracking. Even though they are connected, they are not identical. It is possible to do exhaustive search without using backtracking. Backtracking itself can be done either as iterative backtracking or recursive backtracking. So we have to understand when we have to use exhaustive search in general, when a specific version of exhaustive search, namely backtracking, and when we can use very specifically recursive backtracking. First, exhaustive search in state graph. I start with where we stopped yesterday. The problem is formulated as a search for a goal state in a state transition graph or state space graph. Anything is okay. A problem as a state space search has the following 5 components. There is a set of states. One state is distinguished as initial state or start state. There is a transition model. There is another distinguished state called goal state. We may be either given the goal state or a test using which we can check whether a given state is a goal state or not. And then we are not merely interested in the goal state, we are interested in the sequence of states which take us from the initial state to the goal state. The sequence of states and actions from the initial state to the goal state is the path, and if it is an optimization problem, we are not merely interested in finding a path from the initial state to the goal state, but also in an optimal path, a path with the cheapest cost. So a problem formulated as state space search has the following components. I also told you what is transition model. In every state, there is a set of possible actions, and when we take an action in a state, the agent or we make a transition to the next state or the successor state. That is known as transition model. Okay. The state space may be either a graph or under certain circumstances, it may be a tree. The state is represented by a structure. For now, I am not committing to the structure. The structure may be a sequence. I use the word sequence, you may use the word list, or you may use the word vector, or you may use the word array. Okay. And we want to construct the structure. It is possible to construct the structure, the solution structure, by a sequence of actions or decisions. We may either start with an empty structure and extend it into a complete structure, or we may start with a feasible structure and improve that into an optimal structure. Anyway, I make a distinction between solution and its construction. Solution in general may be any structure. It need not necessarily be a sequence, but it is constructed always by a sequence of actions or decision. If the problem exhibits this nature, the solution structure can be constructed as a sequence of actions, as a sequence of decisions, then we can do exhaustive search for the solution. Okay. And this is how we adapted, we transformed a graph traversal algorithm into an exhaustive search algorithm. I want you to see the connection between, the similarity and the difference between graph traversal and exhaustive search. You may immediately realize that this is simply whatever first search algorithm. Add initial state yes to discovered. There are two data structures. One I call discovered, the other I call explode, or it may be bag. I think it is better to call it a bag. While the discovered is not empty, delete a state from discovered, call it V. What did we do in whatever first search? If V is not already explored, you have to recall what is the difference between discovered and explored. When a node is first discovered, a vertex B is discovered from a node, from a vertex U, we say it is discovered. If all the adjacent vertices of B, such as W1, W2, and W3 are also discovered, then we say it is also explored. That is my terminology, and it is a nice terminology to work with. When V has been discovered through another node, we say V is discovered. When all the adjacent vertices, all the neighboring vertices of V are also discovered through V, we say that it is explored. So B is discovered but not yet explored. We have not used B to discover all its successor states. Then we have to do that. For each successor state W of B, do set the parent of W to B. The successor state W has been discovered from or through V. Now that the successor state W has been discovered, add W to the discovered data structure bag. After we have executed the for loop discovers all the successor states, adjacent vertices, neighboring vertices of V. Therefore, now we have to say that V has been explored. So add V to explode. The only difference is shown in red. If V is a goal state, then print the solution. What is the solution? From the path from start node initial state to the goal state is a solution. Therefore, print V to S path is a solution and return. The algorithm terminates there. While executing the loop, if we did not encounter a goal state at all and the loop terminated, we have to return that there is no solution. So this is simple. We have not done much. We have taken a generic graph traversal algorithm, namely whatever first search, and turned it into an exhaustive search algorithm. What are the differences? This is difference 1. Difference 2 is instead of vertices, we have state. And therefore, consequently, difference 3 is instead of considering the neighboring vertices of V or adjacent vertices of V, we are considering successor states of V. Okay. Take every possible action in V and find out what are the successor states. For each successor state, do this. This algorithm can be slightly improved in efficiency by moving this 5, 6, 7, this part. You can test whether a state is a goal state when we remove that, delete it from the discovered data structure. Or it is also possible here, as you generate a new state, you can test whether W is a goal state. So you can bring it here and say if W is a goal state, then print W to S path as a solution and return. Question for thought. I say that if you move this the logic 5, 6, 7 to this place, the resulting algorithm will be slightly better. Why? Can anyone answer this question? Are you with me?
Yes, sir.
By moving this logic from this place to that place, the algorithm is slightly more efficient. What is the reason?
Sir, it's the algorithm will be more efficient because without moving it as such, we will see that the goal state will be set in discovered bag, sir. Therefore, unless or until we come to the goal state from by traversing one by one from the discovered set or bag, we wouldn't reach the goal state. But whereas if we just push it into the if we not explore then in the for loop, then it means that as soon as the particular goal state discovered, we can say that we have found a way to go to the goal state that is required instead of waiting for it to get traversed one by one in the discovered bag or set.
That's right. May I know your name?
My name is Sandeep, sir. B. Sandeep Shekhar.
Good, Sandeep. Okay, let's go on. And therefore, this is the resulting algorithm. All right. So what we have seen till now, exhaustive search on a state graph. Okay. For some problems, the state space is not a graph, but it is a tree. If the state space is not a graph, but a tree, then exhaustive search reduces to backtracking. We will see how it becomes. As I said, the solution may be a combinatorial object such as a subset or permutation or combination or partition or path or tree. The solution structure need not necessarily be a sequence, but often we may get a solution. A path can be viewed as a sequence of vertices. A permutation is a sequence. A combination is a sequence. A subset can be viewed as a sequence of elements and so on. However, even if the solution structure is not a sequence, if the solution can be constructed as a sequence of decisions, then the graph would reduce to a tree. When the construction structure is a sequence of decisions, the graph reduces to tree. We can represent the construction structure as a vector or array or list or whatever you call it. And we will construct the vector by component-wise extension. Okay, what do we mean by that? We represent the solution by a vector. Vector is a high-sounding word. If you want to use, let us use the word array. So you have y1, y2, y3, and so on, yn. That is a solution. For now, let me not distinguish between solution and the construction sequence. The solution itself is a sequence or an array. We can start with an empty vector. We have not put any values for y1, y2, y3, and so on, yn. The goal state will be a complete vector. We have put values for all the components of the vector or array. y1 we have assigned a value, y2 we have assigned a value, and so on, and finally yn also we have assigned a value. For every yk there is a set of possible values. What are the possible values for the first component, y1? What are the possible values for the second component, y2? What are the possible values for the third component, y3, and so on? What are the possible values for the nth component, yn? Taken individually for yk, we have a set pk of possible values. But taken together with y1, y2, and so on, yk, some of the values which were possible for yk individually may not be possible together with y1, y2, and so on, yk minus 1 because of some constraints. Okay, so for every y1 to yk, pk is constrained to a set of permissible choices. We will use the word possible values and maybe permissible choices or feasible choices, ck. ck will be a subset of pk. How do I distinguish between pk and ck? pk is a set of all possible values for yk, but when you take a partial solution together, yk, some of the values which were formerly possible are no longer possible. Okay, I call them permissible or feasible. I have some dilemma about the terminology. Okay, we are given a partial solution y1 to yk. We want to extend it to y1 to yk minus 1. That means we want to consider every permissible choice for yk plus 1. So as shown here, the state y1 to yk is represented by a vertex. Now we have to choose yk plus 1. yk plus 1, the choices are C1, C2 and so on, C3, resulting in y1 to yk plus 1. When the solution is a vector like this, the state space will not be a graph, it will be a tree. Okay. Suppose there is no permissible choice for yk plus 1. What should we do? If none of the choices for k plus 1 at the component is feasible, then what we would do is extend the k minus 1 size vector with a different choice for kth component. Yk has certain value, we will undo yk with another value. It will become clearer when I demonstrate it with an example. Okay. When the state space is a tree, exhaustive search becomes backtrack. Each state is a partial vector. The vector grows and shrinks like a stack. For a transition from one state to a next state, the partial vector grows. For a transition from one state to the parent state, the partial vector shrinks. And then we call that backtrack. When a complete vector is not a solution, it is possible that we have assigned values for all the components from y1 to yn, but it is not feasible. Then we have to backtrack. Under another circumstance also we will backtrack. When none of the possible values is feasible for extending the partial vector, then also we have to backtrack. We already have y1, yk minus 1, yk. Okay. It is impossible to find a feasible value for yk, then also we have to backtrack. So we backtrack under one of these two situations. We have a complete vector, but it is not a solution. It is a partial vector and it is impossible to extend the partial vector further. Okay. This is exhaustive search. In a state, I have taken the same algorithm that we use for state graph. It may look alike: add initial state yes to bag. While bag is not empty, delete any state from the bag. Right now we are not worried about the order in which we remove a state from the bag. That is why we use the word bag. Suppose we have used tag or queue, that would be different. For now, we are not worried about that. If B is a goal state, then print B2S path a solution and return. For each successor state W of B, set parent of W to B. This is B, W1, W2, and so on. W3, we say parent of W1 is B, parent of W2 is B. We do that for all W. This is a typo. Add W to back. If you recall the earlier algorithm for graph, you will realize the differences. Okay, this part, if B is not in explode, and this part, they are missing. What is the reason for not worrying about that? If B is not already explode, only then you explore B, and after you have discovered all the successor states of B, then mark that B itself is in explode. Why have we not added that? Why do we not worry about exploring?
Sir, because in a tree cycles don't exist.
Right. Because in a tree cycle does not exist. This discovering, once it is explored, there is no need to keep track of which are explored or which are not explored. Think about that. Why no need to maintain explored data set? Okay. This is exhaustive search algorithm. Suppose we have state as a vector. Y. X is the input. State or solution is the vector. Input is an instance X. Output a solution Y if a solution exists, otherwise none. So how do we translate this exhaustive search algorithm to work with a vector as a state? While bag is initialized with the input and this is the solution. Solution is empty to start with. While bag is not empty, choose and delete an X comma Y from B. Remember, we have made a small difference. We are not only maintaining the partial solution Y, we are also maintaining the remaining input. X is the remaining input. The remaining input may be needed to calculate the set of feasible choices for the next component. Okay. So X comma Y is the X is the remaining input and Y is the state that we have deleted from the bag. Suppose we can extend the partial solution Y by a single component. When we extend Y by a single component, the remaining input will also be reduced. Okay. Let X super 1, Y super 1, X, I call that superscript as super, X super 2, Y super 2, and so on, X super K or whatever it is, not K, K is not a. These are the possible extensions of XY. Extended by one step, by one component. For each feasible one component extension, X super I, Y super I of XY, what do we want to do? If X super I, Y super I is complete, that means Y has become Y1 to Yn. Return the solution derived from X super I, Y super I. If it is not complete, then add X super I, Y super I to the bag. That is how we are translating the exhaustive search algorithm when the state or the solution is a vector. If the loop terminates, then that means there is no solution. Okay, and finally, exhaustive search in a state tree with recursive backtracking. Okay, I start with recursive DFS in a graph. I'm only recalling the algorithm. We have already seen that. Add vertex V to explode. Then we are discovering all the neighbors or adjacent vertices of V for each edge VW in the edge set. If W is not already explored, then do recursive DFS on W itself. When it is a tree, the recursive DFS reduces to this. There is no need to maintain explode. All that we have to do is for each edge VW in E, if W is not a leaf, we can do recursive DFS. Note that this is the base case. Okay. How does it translate to exhaustive search? Algorithm search, X is the remaining input, Y1 to Yk minus 1 is the partial solution. satisfying the constraints given. The problem may be given constraints such as an 8 queens problem. The positions for k queens we have chosen should be safe. Output complete solutions y1 to yn which can be extended from y1 to yk minus 1. Satisfying the constraints have been printed. All right. Extend x comma y1 to yk minus 1 to all feasible x dash y1 to yk. We have already assigned values for k minus 1 components. Extend the kth component by assigning it a value. For each feasible choice c for yk, we want to assign a feasible value to yk, satisfying the constraints. Okay, yk becomes c. Then, if x dash, the remaining input, and y1 to yk is complete, then print the solution y1 to yk. Since it is complete, actually it should be y1 to yn and return. Else, if it is not complete, then you have to do search x dash y1 to yk minus 1. This else is not really needed because the if class, in the if class, the last statement is returned. This is a very simple algorithm, recursive backtracking. How does it work? Let us assume that we have a three component vector x1, x2, x3. x1 has two possible values. I will denote that by x11, x12. x2 has two possible values, x21, x22. There may be any number of values. x3 has two possible values. To start with, the solution vector, the state vector, solution vector and state vector are the same, is x11. Okay. Now we have to extend it to x2. Therefore, now the partial vector is x11, x21, and the state tree grows like this. You should remember that the state tree is not an explicit tree data structure, it is only an implicit tree discrete structure. Okay, now we have to extend it to x3, x31. Suppose now we have a complete solution. x11 is a partial solution, partial vector. x11, x21 is partial vector. x11, x21, x31 is a complete vector. But if it does not satisfy the constraints, the properties given in the problem, we have to backtrack. What do we mean by backtrack? Okay, we undo the value of x31. Are there any other choices, feasible choices? Yes, there is a x32. Therefore, what we actually have done is and then we went up and come back here. This is again a complete solution. Suppose this is also not a complete vector. Suppose it is not a solution, then we have to backtrack again. How do we backtrack? Okay, we have tried all possible values for x3, x31 and x32. Therefore, we have to try another value for x21. Is there another value? Yes, there is x22. So now we have a partial vector x11, x22. How do we extend? We can extend that with x31. Suppose this is not a solution. Extend that with x32. Suppose that is also not solution. So what should we do? What should we do now? We will now this is the path is a solution x11, x22, x32. We have to go up. And is there any other value possible for x2? No. Then we have to go up. Is there any other value possible for x1? Yes. x12 is possible, and therefore, oh, okay, sorry. I'm assuming there are 3 possible values for x2. x21, x22, x23. So try next feasible choice for x3, next feasible choice for x3. These are complete vectors, but not solutions yet, suppose. Now we have exhausted all possible values for x2. Therefore, we have to check if there is another possible value for x1. Yes, there is a x12, and so on. x21, x31, x32, x22, x31, x32, x23, x31, x32. In fact, if it is an optimization problem, we have to traverse the entire state tree. This is a state tree. Only after we have traversed the entire state tree, we can say something is the optimal solution. Okay, this may be a solution, for example. Suppose x11, x22, x32 is the optimal solution. But we should not stop there. Maybe x12, x21, x31 may be a better solution. So we will hold that as a solution. Maybe after that x12, x23 and x31 may be still better. Therefore, if it is an optimization problem, we should not stop with finding a solution. We have to traverse the entire state tree, and only then we can say with conviction that this is the optimal solution. On the other hand, if it is a search problem, suppose x11, x22, x32 satisfies the constraints. As soon as we have found a solution which satisfies the constraints, we can immediately terminate. There is no need to continue traversing the state tree. So note the difference between how the state tree is traversed for a search problem, for solving a search problem, and how the state tree is traversed for solving the optimization problem. In all these, as we traced, you would have realized that the solution vector, it grows. Then as we backtrack, it shrinks. It again grows. When we backtrack, it shrinks. Here, from x11, x22, x32, it would shrink to x11, x223. Oh, if there is no more value, there is no feasible choice for x2, it will shrink to x11. Okay, then it will try x12 and so on, and that is what we have shown here. So the solution vector or the state vector keeps growing and shrinking like a stack. That's all. Now maybe homework you should visit. Number 1, use 8 queens, use recursive backtracking to solve 8 queens problem. 2, use recursive backtracking to solve traveling salesman problem, TSP. I stop here.